Okay, so this video is not going to it's not going to be going through a specific section in the book. Instead, it's a video or it's a topic that I wanted to throw together myself just to establish some connections between what's happening in the first three chapters. So chapters 1 and 2 are very algebraic in nature. We're focusing on solutions to linear systems and determinants of matrices, properties of matrices, things like that. And then chapter 3 is about vectors, and we talk about some geometric properties of vectors, equations of lines and planes. We did establish some connections between matrices, systems of equations, and kind of a geometric interpretation of those things, planes and lines and what have you. But in this section, I want to go into more depth on what some of these things represent. So the primary thing that we're going to be using, the main tool that we're going to use here to explore these ideas is what's called a linear transformation. In a number of ways, you can kind of call linear transformations the major idea of linear algebra, but I sort of hesitate to say that there's just one main idea in linear algebra. The reason I say that, though, is pretty much every topic that we talk about in this course can be viewed from the perspective or framed in terms of linear transformations. Now, we're going to define a linear transformation in a specific way in this video, in this series of videos, but chapter 8 of our book is the chapter that handles linear transformations in kind of fuller generality. So what I'm calling a linear transformation here is kind of a little more specific than the general definition that we're going to give in chapter 8. However, by the end of chapter 8, we will have shown that our general definition is actually characterized by this one. That's all very vague, and it shouldn't make a whole lot of sense quite yet, so don't worry too much about it. Let's just proceed with what we have here. So let's suppose that A is an m by n matrix, and we're going to use the matrix A to define a function that takes vectors from Rn as inputs and produces vectors in Rm as outputs. We're going to call that function T of A, and the way that T of A works is by plugging the vector x into T of A. The output is Ax. Now, in order for this to make sense, the vector x has to be thought of as a column vector. So, if A is this matrix here, A1, 1 through AMN, I'm not even going to write in everything there, then we would think of x, so here's my A, I want to think of x as a column vector, x1 through xn, and by the way multiplication of matrices with vectors works, the output is going to be some m by 1 vector. So that's bm down there, but that's what A times x results in. Okay, and if I wanted to be more careful, I'd actually write the dot products of all these rows and entries and stuff or rows with this column here. I'm just going to call them B's just to keep things simple. But again, this would be like the input vector x, and this would be like the output vector that I get from multiplying A times x. So we're viewing A as a function of sorts. Again, takes vectors from n space and maps them into vectors in m space. And we called this type of a function a linear transformation. Again, we will give a more general definition of linear transformation that will look much different in chapter 8, but we'll establish the connection as we work through that chapter. Now, even though this can be defined for any m by n matrix, regardless of its size, to get a sense of the geometry of these linear transformations, we're going to focus primarily on 2 by 2 matrices. And I say or 3 by 3, I'm going to just do some passing mention of some 3 by 3 cases. Okay? So let's think about what this would look like if A was a 2 by 2 matrix. Well, if A was a 2 by 2 matrix, then this linear transformation, this function, T of A, is going to take vectors in 2 space and map them to other vectors in 2 space. So it keeps us in the same Euclidean space. It keeps us in the plane when we look at our input vectors compared to our output vectors. Similarly, if A was a 3 by 3 matrix, it would be taking vectors in 3 space and mapping them to other vectors in 3 space. So let's sort of illustrate this with an example. Like I said, pretty much everything we do in this video and the ones that follow are going to be for 2 by 2 matrices specifically, because it's the easiest case to visualize. So let's let A be this matrix right here, 3, 1, 0, 3. And I have this vector x, which is the vector 1, 2. I want to sketch 2 vectors, this one, x, and then ta of x. In other words, the output vector that we get by plugging in x. So x, if x is 1, 2, the vector 1, 2 has a horizontal component of 1, a vertical component of 2. So as a position vector, x is going to look like this. That's x right there. Okay? Now if I wanted to graph or sketch the vector that I get by plugging x into this transformation, well, ta of x is equal to our matrix A, 3, 1, 0, 1, times the vector x, 1, 2. And what does this come out to? Well, that's going to be 3 plus 2, which is 5. And then I get 2 down here. Horizontal component is 5, vertical component is 2. So here's 5, 2. Gives me this vector. Kind of like that. Okay, so that is ta of x. Oftentimes we're going to think of this as an input vector, and this as our output vector. Okay? So again, we think of this function as transforming our input vector into a new vector, this output vector. Okay? Let's keep going with this idea. So we're going to do another example. So we're going to let A and X be the same matrix and same column vector that we talked about in the previous example. But this time, I want to think of these two vectors in terms of linear combinations. So X, remember, was the vector 1, 2. And in this plane, what I want to do is represent or re-sketch vector x. So it's 1, 2, it looks like this. There's x. And we want to represent this as a linear combination of the basis vectors I and j. So remember, this is vector I. Vector j is this guy, but if I were to look at the vector 2j, that's the vector that scales j by a factor of 2. And you can see from this picture that I plus 2j is equal to our vector x. I plus 2j equals our vector x. Okay, so what I did is I broke x down into a linear combination of our standard basis vectors, I plus 2j. Okay, now what I want to do is basically the same thing with the output vector that I got over here, but rather than represent the output vector as a linear combination of I and j, like I did here, I want to take I and j and put them into our linear transformation first, see what those look like, and then represent the image of this vector, the output vector associated with this input vector as a linear combination of those. So let's find ta of I and ta of j. Ta of I is going to be my matrix A, which is 3, 1, 0, 1, times the vector I, which is 1, 0. Now notice, when you dot each row of this matrix with this column vector, you're only going to end up with 1 times the entry in the first column each time. 1 times 3, and 1 times 0. Okay? This is extremely, extremely important, and we're going to use this idea in what we do later. But before we elaborate on that, let's do the same thing. TA of j. Let's evaluate that. This is our matrix A, 3, 1, 0, 1, times our column vector j, which is 0, 1. Notice in this case, the 0 will just give me zeros when I multiply to my first column. My second column, each entry is going to be multiplied by a 1, and I get 1, 1. So interestingly enough, when I'm using standard basis vectors, if I multiply I by a matrix, the result is just the first column of the matrix A. And if I multiply J by this matrix, the result is the second column of that matrix A. And that had nothing to do with this specific matrix. That would have been true regardless of what this 2 by 2 matrix was. Multiplying by I always gives me the first entry. Multiplying by J always gives me the first column. Multiplying by J always gives me the second column. That's, hopefully you can see why that would be happening. So what I'm going to do, I just plugged I and J into this linear transformation. And what I've done is I've transformed my standard basis vectors into a new pair of vectors. I'm going to graph those. So the first one is 3, 0. Okay, that would be the same thing as 3 times I. So that's going to look like this. That's the vector 3, 0 right there. Okay, and now if I wanted to graph the second one, it's the vector 1, 1. That guy right there is the vector 1, 1. Okay, what was I supposed to do with these? Well, I wanted to represent my output vector from the previous example, which was the vector 5, 2. So let's draw 5, 2 again, or sketch that in there. 5, 2 would be here. Just kind of go like that. Okay, and I want to represent this vector as a linear combination of these two vectors. And it may not be immediately obvious how to do that, but notice if I were to double the length of this one right here, like that, and then if I were to construct a parallelogram out of these two vectors, the one that I just got by doubling 1, 1, so I got 2, 2 here, and then doubling this guy, I would end up with that parallelogram. Notice my output vector from before already turns out to be the diagonal of that. So how do I represent that in terms of a linear combination? Well, notice the image of my vector I, or the output that I got from plugging I into my linear transformation, didn't have to be scaled at all. So that image, or that output, I can just call TA of I. What did I have to do to this vector? Remember, this initial vector right here, 1, 1, was the output that I got from plugging J into my linear transformation, but I had to double its length. I had to multiply by 2, and I got this. Summing these two vectors gives me this output vector, which is the same thing as TA of x from the previous example. Now compare these two linear combinations. Specifically, look at the coefficients. The coefficient on this first term is a 1, and the coefficient on this second term is a 2. What does that mean? Well, what this tells me is that the vector x, when written as a linear combination of the standard basis vectors I and j, can then be plugged into our transformation, giving me the TA of x, the output vector. And that output vector can be written as a linear combination of the outputs of I and j with the same coefficients that I would have used in this linear combination. What that essentially does, and again, this was not a coincidence. This was one vector that we looked at, but we're going to show in the next theorem that this will be true for any linear combination of vectors that I can create here. The output of any linear combination will be a linear combination of the outputs of each vector that I used here with the same coefficients. So that basically says that whatever the transformation does to I and j specifically will encode all of the information that we need to determine the transformation of any other vector in 2 space. That might be a tricky thing to wrap your mind around right now, but let's go ahead and talk about this theorem, and then hopefully we can start making more sense of that. Okay, so again, we're going to let A be any m by n matrix, and this looks very messy, but it's actually very simple what we're doing from step to step. It's just a lot of notation. Let's suppose that we have k vectors that we chose from Rn, v1 through vk, and then we're going to let c1 through ck be scalars. And I use these to form a linear combination. What happens if I plug this linear combination, which would be another vector in Rn once you evaluate it, into my linear transformation T of A? Well, I want to show that the result of plugging this linear combination of vectors into T of A is going to give me something equivalent to a linear combination of the outputs of V1 through VK in this linear transformation, where the coefficients on those terms all are exactly the same as the corresponding coefficients here, C1 through CK, C1 through CK. The coefficients don't change. Okay, so this follows from basic matrix properties that we've already talked about. What does TA of this input actually mean? Well, it means that I multiply this input on the right or on the left by the matrix A. But A, we know, since this is now matrix multiplication, which has the distributive property, I can distribute A over each individual term. By my homogeneity property, scalars can be brought out like this. And then if you look at what remains, AV1, AV2, and so on, each one of these is the result of plugging V1, V2, and so on into our linear transformation T of A. AV1 is what TA of V1 means, right? So that establishes this theorem. Okay. Actually, before I jump into that, I just want to review one thing here, something I emphasized in this example. So again, remember, when you're looking at these linear transformations, which is just A times whatever vector I put in here, when you evaluate these linear transformations at standard basis vectors, specifically I and j, the result is the first column and the second column, respectively. So what that means, you've heard me use this term a little bit here. I keep saying the image of a vector. When I say the image of something, I'm talking about its output. And that's a really helpful term to have here, so I want to talk about that for a second. If I plug a vector x into my linear transformation, its output, TA of x, can also be called the image of x. It's what happens after plugging something into a linear transformation. The term image is also used for sets of vectors. Let's suppose I had an entire region, maybe a circle in here, and all of the points in that circle might correspond to terminal points of some vectors, some position vectors. If I wanted to plug all of those vectors for that region into this linear transformation all at once, then the output vectors would form some other region over here, some transformed version of that region. Maybe that circle would be squished into an ellipse over here, or maybe it would be stretched out in some way, or skewed in some weird way. We would say that that new region over here is the image of the old region after using this transformation. Okay? So let's combine some of these facts into something that we can use. All right, so here the notation might be a little bit tricky, but we're talking about partitioned matrices here, so hopefully we've had enough practice with it with that idea that you can understand this. Suppose A is a 2 by 2 matrix. Then what we showed in that previous example was that if you multiply A times your standard basis vector I, the result is just going to be the first column of whatever A was. So in other words, plugging I into your linear transformation T of A just gives you the first column of A. And plugging J into T of A just gives you the second column of A. So what that means is you can construct A out of those images, the image of I and the image of J under this linear transformation T of A. So basically, what that linear transformation represents is the images of those standard basis vectors as columns of that matrix. We're going to practice that idea in a minute. If it's a 3 by 3 matrix, so we're transforming vectors in 3 space, then the first, second, and third columns of the matrix would correspond to the images of I, j, and k. You have 3 standard basis vectors there. Okay. Furthermore, if A is a 2 by 2 matrix and you want to multiply it on the right by any column vector x, so I'm keeping this general now, x1, x2, then from the way that we characterized matrix multiplication back in section 1.3, remember we gave a bunch of equivalent characterizations of it, we showed that if you multiply a matrix by a column vector on the right, then you can write that matrix multiplication as a linear combination of the columns of your matrix A, where the coefficients are just the entries of this matrix. We did a quick little derivation of that, and we haven't really used that much yet, but here's the first place where that's kind of becoming relevant. Okay, so what does that tell us? Well, if you want to evaluate the image of any vector in 2 space or 3 space or whatever space, this generalizes. If you want to calculate the image of any vector, all you actually need to know are the images of your standard basis vectors, because then you can form a linear combination of those to get this. All right, so let's look at some examples. I'm going to say that we have this linear transformation that maps R2 into R2. And it's going to be a function that takes input vectors and rotates them 90 degrees counterclockwise. Okay, and if we can assume that T of A is a linear transformation, which it is, we're going to take that fact for granted here. I want to find the matrix A. So again, just because we can define a function that transforms one vector in R2 into another vector in R2, that doesn't necessarily mean that that function is a linear transformation. Because there are other functions that will do the same thing, take vectors and map them to other vectors, but there's no way to represent that function in terms of a matrix times the input vector. That's what makes this a linear combination, or sorry, a linear transformation. However, it turns out that this transformation, which rotates vectors by 90 degrees, does happen to be a linear transformation. And we're just going to take that for granted and find A as a result. So how do we do that? We start by thinking about your standard basis vectors. Here's I, here's J. Okay? Now, like we said up here, the output of any vector under a linear transformation can be determined by simply knowing the outputs of your standard basis vectors under this transformation. So if I map these vectors using the transformation T of A to other vectors in R2, where does I go and where does J go? Well, remember, the purpose of this linear transformation is to rotate vectors 90 degrees. So that means I is going to be mapped here. That makes this TA of I. And J is going to be rotated onto the negative x-axis. So TA of J is going to be down there. Okay? But that means TA of I is equal to, in component form, which we're going to write as a column vector, 0, 1. And TA of J, based on where I just sketched this thing, remember it still has a length of 1, because all I did was rotate that vector. It's now going to have component form -1, 0. According to the work that we just did, the matrix for this linear transformation is the matrix that has these 2 vectors as columns. 0, 1, -1, 0. What does that accomplish for us? Well, now if I want to take any vector in R2 and perform the same transformation on it, if I want to take any vector at all and rotate it 90 degrees, and then determine what would the component form of that new vector be after doing that rotation, all I have to do is take that vector and multiply it on the left by this matrix A. It will do that for any vector now, and all I needed to determine was how this transformation affected these two standard basis vectors. Okay, we have more examples to do to build on this, but we're out of time in this video, so that'll be in part 2.